What are distribution transformers? Defining the role of distribution transformers. Distribution transformers are the unsung heroes at the tail end of the vast electrical power distribution network. Their primary and indispensable function is to take the relatively high-voltage electricity traveling along distribution lines and reduce it to a lower, safer, and more usable voltage that can power our homes, businesses, and industries. These transformers act as the crucial interface between the utilities' distribution infrastructure and the consumer's electrical systems, ensuring that the electricity delivered is compatible with the appliances, machinery, and equipment we rely on daily. Unlike their larger counterparts in transmission substations, distribution transformers are strategically positioned closer to the end users, often mounted on utility poles or placed on the ground in protective enclosures. The necessity of voltage step-down. The necessity for stepping down voltage at the distribution level stems from the inherent advantages of transmitting electricity at higher voltages over long distances. Higher voltages allow for the transmission of the same amount of power with lower currents. This reduction in current significantly minimizes energy losses due to the resistance of the transmission lines, I2R losses, making long-distance power transfer more efficient and cost-effective. However, these high transmission and primary distribution voltages are far too dangerous and incompatible for direct use in homes and businesses. Therefore, distribution transformers are essential to safely and efficiently reduce these voltages to the standard utilization levels required by electrical devices. Operating under fluctuating loads. A defining characteristic of distribution transformers is their operation under constantly varying load conditions. Throughout the day and night, the demand for electricity from residential, commercial, and industrial consumers fluctuates significantly. During peak hours, such as evenings when most people are home, the load on distribution transformers increases substantially as lights, appliances, and machinery are in use. Conversely, during off-peak hours, such as late at night, the demand drops considerably. Distribution transformers must be designed to handle these dynamic load changes efficiently and reliably, ensuring a consistent supply of power to consumers regardless of the overall demand. Efficiency considerations at partial loads. Given their continuous operation and the fluctuating nature of the loads they serve, the efficiency of distribution transformers at partial loads is a critical design consideration. While all electrical transformers exhibit maximum efficiency at or near their full rated capacity, distribution transformers are specifically engineered to maintain high efficiency even when operating at significantly less than their maximum kVA rating. This is crucial for minimizing energy losses over the long term, as these transformers are energized 24 hours a day, 7 days a week. Advanced designs, including those with amorphous metal cores, further enhance efficiency at partial loads, leading to substantial energy savings over the transformer's lifespan. Maintaining stable output voltage, voltage regulation. Another vital function of distribution transformers is to maintain a relatively stable output voltage despite the variations in the load. Consumers expect a consistent voltage supply to ensure the proper operation of their electrical equipment. Significant voltage drops under heavy load conditions can lead to malfunctioning appliances, reduced lighting intensity, and potential damage to sensitive electronic devices. Distribution transformers are designed with good voltage regulation characteristics, typically expressed as a percentage change in voltage from no load to full load conditions. A lower percentage indicates better voltage regulation, ensuring a more consistent and reliable power supply to the end users. Common kVA ratings and applications. Distribution transformers come in a wide range of kVA, kilovolt-ampere, ratings to cater to diverse load requirements. For residential areas with individual homes, smaller single-phase transformers with ratings ranging from 5 kVA to 50 kVA are commonly used. Commercial establishments, such as small businesses and retail stores, might require larger single-phase or three-phase transformers ranging from 75 kVA to 300 kVA. Industrial facilities with heavy machinery and significant power demands typically utilize three-phase distribution transformers with ratings extending from 300 kVA up to several thousand kVA, although units above 5,000 kVA might sometimes be classified differently based on specific standards. The selection of the appropriate kVA rating is crucial to ensure efficient operation without overloading the transformer or experiencing excessive voltage drops. Different mounting configurations. Pole-mounted transformers. Pole-mounted transformers are a familiar sight in suburban and rural areas, where they are installed on utility poles to serve overhead distribution lines. These transformers are typically smaller in size and capacity, often single-phase units ranging from 5 kVA to 75 kVA, designed to supply power to a limited number of residential customers or small commercial establishments. Their elevated mounting helps save ground space and provides a degree of protection from flooding and accidental contact. However, they are also more exposed to weather elements and can sometimes be aesthetically less appealing in residential neighborhoods. Different mounting configurations. Pad-mounted transformers. In contrast to pole-mounted units, pad-mounted transformers are installed on the ground, enclosed in a secure, tamper-proof steel cabinet placed on a concrete pad. These transformers are commonly found in underground distribution systems prevalent in urban areas and modern residential subdivisions. Pad-mounted transformers are generally larger three-phase units, ranging from 75 kVA to 2,500 kVA or more, serving a larger number of customers or larger commercial and industrial facilities. Their ground-level placement offers enhanced safety, improved aesthetics by eliminating overhead lines, and better protection from environmental factors. Single-phase versus three-phase distribution transformers. Distribution transformers can be either single-phase or three-phase, depending on the nature of the load and the distribution system. Single-phase transformers are primarily used to supply power to residential customers and small commercial loads, delivering a single alternating current waveform. Three-phase transformers are designed to supply power to commercial and industrial facilities that require higher power levels and often utilize three-phase machinery and equipment. Three-phase systems offer advantages in terms of power delivery efficiency and the ability to run large motors more effectively. Internal connections, delta and star configurations. The primary and secondary windings of distribution transformers are typically connected in either a delta or a star Y configuration, depending on the specific voltage transformation requirements and the need for a neutral point. The primary winding is often connected in a delta configuration, which provides a closed loop and allows for three-phase power to be applied. The secondary winding is frequently connected in a star or Y configuration, which provides a neutral point that can be grounded, offering a reference for single-phase loads and enhancing system safety. The combination of delta and star connections, example delta star or delta Y, is common in distribution transformers to achieve the desired voltage step-down and provide a stable neutral. Cooling methods. Liquid-filled transformers. To dissipate the heat generated due to energy losses within the core and windings, distribution transformers employ various cooling methods. Liquid-filled transformers, the most common type for outdoor applications, utilize an insulating liquid, typically mineral oil or a synthetic ester, to immerse the core and coil assembly. This oil acts as both a dielectric, insulating medium, and a coolant, transferring heat away from the active parts through convection and conduction to the tank walls, which may be equipped with cooling fins or radiators to further enhance heat dissipation. Liquid-filled transformers offer excellent cooling and insulation properties, making them suitable for a wide range of applications and power ratings. Cooling methods. Dry-type transformers. In contrast to liquid-filled units, dry-type transformers rely on air or other non-flammable gases for cooling. The core and windings are exposed to the surrounding air, which circulates naturally, and air natural, or is forced by fans, AF, air forced, to remove heat. Dry-type transformers are often preferred for indoor installations, particularly in environments where fire safety is a significant concern, such as hospitals, schools, and commercial buildings. While generally having lower power ratings compared to liquid-filled transformers for the same size, advancements in insulation materials have expanded their application range. The importance of distribution transformers in everyday life. In conclusion, distribution transformers are indispensable components of the modern electrical infrastructure, playing a critical yet often overlooked role in our daily lives. They are the vital link that safely and efficiently reduces high-voltage electricity to the usable levels that power our homes, businesses, and industries. Their ability to operate reliably under fluctuating loads, maintain stable output voltage, and minimize energy losses makes them essential for a dependable and cost-effective electricity supply. From the pole-mounted units in rural landscapes to the pad-mounted enclosures in urban centers, distribution transformers are the workhorses of the power grid, ensuring that the pearl of the modern age, electricity, is readily available at our fingertips.